I'm Sebastian Estlund, and I'm here to tell you all about CollabFuzz, a framework for collaborative fuzzing. So fuzzers have become an essential tool of any modern software development lifecycle. So the problem nowadays is that you have a bunch of these fuzzers, and which one should you actually run for your project? Well, with CollabFuzz, we tackle this problem in a slightly different way. We simply allow you to run all of them together to even out the difference between the fuzzers so that they can help out each other. And yeah, CollabFuzz takes care of this orchestration of these different fuzzers for you. So let's take a step back and have a look at what collaborative fuzzing actually is. So typically what you have is you take one fuzzer, let it run for your target program, and it generates inputs and possibly finds crashes. If you need to scale it up to get it to run a bit more quicker, you simply run a bunch of these instances of the same fuzzer in parallel and let them run in the so-called sync mode that most of the fuzzers support. However, in 2019, there was this paper published at Usenet Security called nfuzz, where the authors proposed an idea of having different, like a diverse set of fuzzers work together. So, and the intuition behind this is that, okay, certain fuzzers can get stuck at a point in the program, but if you have a diverse set of different fuzzers, they might get unstuck and help each other out so that they actually reach more coverage than what they would reach individually. This is where CollabFuzz enters the picture, right? So this is our orchestration framework for running these large-scale collaborative fuzzing campaigns. So CollabFuzz allows a central manager to orchestrate many different fuzzers. At the moment we support AFL, AFL Fast, AFL++, FairFuzz, HongFuzz, so on, so on. Like, you can add more and more fuzzers as you like. The nice thing about this orchestration framework is that it has a central manager which can track the state of all the individual fuzzers and have a global overview of what all these different fuzzers do. You can perform analysis of the state at runtime, so you can see what progress certain fuzzers are making and see which one is better suited for the task, and even implement scheduling policies on top of this. So here's an overview of the CollabFuzz framework. So in essence, the heart of it is the central manager, like the manager container seen here, where you have incoming test cases from the fuzzers which run a certain analysis pass that generate some information for that seed. So for example, coverage and so on, taint information. Then it stores all these incoming seeds. These are then sent to a scheduler, which can schedule out test cases to different fuzzers based on the insight from these analysis passes. So think of like, suppose you only want to hand out test cases that actually trigger new coverage. You have a coverage gathering analysis worker which says, okay, keeps track of the global coverage of the campaign, and then lets the scheduler send out new incoming test cases if it actually found new coverage. So the scheduler part sends out the test cases to the different fuzzers which run in a container, and each fuzzer has a small driver which communicates with the framework, which allows us to actually send out test cases over the network. So why did we implement something like this? Well, we wanted to have a look at scheduling policies in a collaborative fuzzing framework. So nfuzz introduced this notion of having different fuzzers working together, but we want to see, okay, can we actually improve this by selectively handing out test cases to different fuzzers? So we implemented a bunch of scheduling policies. So first of all, we replicated the nfuzz scheduler, which basically sends out all new incoming test cases with new coverage to all the fuzzers at certain intervals. Our implementation in a framework allows us to also do like the same thing, but in like a broadcast sense, where if a new test case comes in and it has new coverage, it immediately sends it out to all the fuzzers. And nfuzz did this periodically every X amount of minutes, simply because it needs to run some analysis when these things come in. And we can do this reactively, so there's no need to wait to do a hard sync. We also implement a few of other scheduling policies. So one thing to highlight is the cost or cost-benefit scheduler that we have, which simply keeps a priority queue of the seeds that it should hand out to the fuzzers. And this one is sorted by some heuristic if you want more detail on these heuristics, have a look at the paper. But in essence, in such a scheduling setting, what you can do is you can schedule on two planes, right? So you can schedule temporarily, so when to send out the test case. So for example, you can delay sending out the test case for a few minutes if you think, okay, it's not useful for the fuzzer to work on it at the moment. Or you can do a spatial scheduling to say, okay, selectively hand out certain test cases to certain fuzzers. So think of an example here, so like you can hand out, like if you have a test case which has a branch that you know is hard to solve, you might want to hand that one out to symbolic execution while you hand out other test cases to a more lightweight fuzzer. So we implemented a bunch of these scheduling policies and so on, and in the end we found out we could not find any statistically significant improvements based on these scheduling policies. So what are the reasons for this? Well, first of all, the main issue is the interface with the fuzzers. So since we take common off-the-shelf fuzzers like AFL and HongFuzz and so on, we don't have any direct control over what the fuzzers are actually doing. We hand out test cases to them and hope that they actually start working on these test cases, but there's no guarantee that they actually work on that one. And then there's also the other issue that might be an issue is that we maybe didn't look at the right features for scheduling. We tried out a bunch of different things, so we couldn't find any super any features that could easily discriminate between the fuzzers. But yeah, the main issue is the interface issue that we don't have a control over what the fuzzers are actually doing. So it's kind of a negative result, but there's some brightness in the future, right? So we have some future ideas of how to improve this. So first of all, we can look at the scheduling in a different light, right? You can do scheduling of resources rather than test case scheduling. So what we could do is say, okay, you have a certain set of fuzzers and let them run, and maybe if you have a fuzzer that doesn't make progress for a while, you let it sleep for say a few minutes and then start it up again and let it go on. That's one of the future approaches. The second one is to add more fine-grained control over the fuzzers so that we can actually target what a certain fuzzer is solving at any particular moment. Of course, this requires modifying the fuzzers that we have, which would be quite some work. So the nice thing about the CollabFuzz framework is that you can easily use this for evaluating new fuzzers. So we created this nice framework which collects all these test cases coming in from different fuzzers, and it allows us to reliably repeat experiments, and actually that's why we could see that there was no statistically significant difference between these scheduling policies that we had. It allows you to do large-scale experiments on a cluster, since the framework can hand out test cases to different fuzzers over a network connection. So you can simply have one CollabFuzz manager in your cluster, and then you run like hundreds of fuzzers that are controlled by the CollabFuzz framework. And a nice thing about this is you can do real-time analysis of your fuzzing campaign. So since we have these analysis passes that can run on incoming test cases, you can visualize the current progress of your fuzzing campaign, which can be quite neat. As I already mentioned, these analysis passes run when a new test case enters the framework from one of the fuzzers. So one of the drivers of the fuzzer sends in a new test case to the central manager. And then these are reactively run to get some analysis information. So to give you an idea of what these analysis passes typically do is one of the typical use cases to get the coverage, right? So it runs the instrumented version of your target program and gathers the coverage. The nice thing is we can store this in a database and then aggregate it over the different fuzzers to see what the difference is between different fuzzers. Another nice thing about this analysis pass implementation that we have is that you can do some pipelining. So you can say, okay, do taint tracking if there's new coverage. So based on results from an earlier pass, you can decide what the behavior is or which passes to run. So it makes it quite flexible. You can express a lot of different ideas with this framework. So to give you an overview of what kind of analysis pass we implemented, obviously in the coverage one, we also implemented some to get the taint information of branches. We implemented a custom one to have a look at like how many instructions are executed before a certain target branch. We can aggregate like global data, as I already mentioned, per fuzzer data or per test case data. So you can actually narrow down like this, all you collected data from this collaborative fuzzing campaign and split it up per fuzzer or however you like, which enables you to generate some nice plots like the ones you can see here. So these are some things we used to see, like the feasibility of the schedulers that we had. So you could actually see like it showed some promise in the beginning, but yeah, as I said, like the interface we have to the fuzzers is the limiting factor here. So to give you some technical information about how this framework is implemented. So each fuzzer needs a driver, right? So we take an off-the-shelf fuzzer like AFL and then add a driver which communicates with the framework. So this is a small program that monitors the status of the fuzzer. So in the case of AFL, we wrote a generic one for all AFL-like fuzzers, which just listens to the newly generated test cases. You can write your own driver or even embed it into the fuzzer if you like. So these drivers communicate with the framework over 0MQ, so it can communicate over the network. So this allows us to do large-scale distributed fuzzing. And for your interest in this, the framework is implemented in Rust and the driver is implemented in Python. So I already mentioned that repeatability of experiments is one of the nice features of this framework. So what we can do is set up a fuzzing campaign with these nice YAML files, as you can see here. So basically you specify the targets you want to run. So here we have like two different binaries that we want to target in our experiment. You set some parameters of the experiment. So for example, the timeout, how many times to repeat the experiment and so on, which scheduler to use. And then finally you specify which configuration of fuzzers you want to use. So in this instance, we have one instance of QSIM, one instance of libfuzz, and two instances of HongFuzz, all working together in a collaborative setting. The fuzzers and target, like the target binaries, are run in Docker containers. And when you specify these files, like in this YAML file, we have some tools to generate Docker Swarm files, Docker Compose files, so you can easily run these campaigns on a cluster if you have a Docker Swarm cluster or Kubernetes. Another thing which I might have already mentioned, but it's like from the analysis passes, we can log everything, right? So later you can query this database where we dump everything and all the decisions made by the scheduler. So you can have a look back at, say, okay, we have some interesting thing going on here. Let's query the database to see what decision the scheduler made and what the output of these analysis passes was. Simply so you can do some nice analysis, which enables you to get more robust results, I guess. So back to an overview of the CollabFuzz framework. We have seen how we have like a central manager, the CollabFuzz central manager, which has some analysis workers. So these different analysis workers react to incoming test cases from the fuzzers. These analysis workers, for the record, you can also distribute them over different nodes, so they can also communicate over the network with each other. So it should scale pretty well. These analysis workers, they obviously analyze the incoming seeds. They run it through some instrumented version of the target program. Then it gives some information to the scheduler, which then decides, okay, let's see, should I hand out this test case to all the fuzzers, or to which fuzzers should I hand it out? So it's a very flexible framework that allows you to express all of these kind of scheduling policies quite easily. So CollabFuzz was part of this larger project where we have like a collaborative fuzzing run. Like we have CollabFuzz the manager, but we also had some previous work published at ECSEC 20, where we have a prediction engine to say, okay, which fuzzer should I actually use in a collaborative fuzzing setting? So if you're interested, have a look at our paper called Cupid. Next, I'll give you a quick demo of the CollabFuzz framework to give you a more concrete idea of how you can use this for your research. Okay, let's have a look at the CollabFuzz framework. So here on the left, we have the GitHub repo. So let's have a quick overview of how you can set it up. So we have some Docker files to build it all. You can also pull in the Docker images from our repo. So the main framework is in the framework folder, obviously. And as I already mentioned, it's written in Rust. So let's have a look at the schedulers. That's the first thing I wanted to show you, how to implement some of these schedulers. So as you can see, we have a few of these schedulers implemented. So let's have a look at, I think the easiest one, the random scheduler. So it hands out test cases to a random fuzzer. So as you can see, it doesn't take up much space to implement one of these. So it's in 44 lines. We have like one of these schedulers. So we have this scheduler trait that you have to implement for your scheduler, and that's about it. So if we quickly look at this one, so here on line 36, we get the number of get all the available fuzzers from the framework. So it gets all the fuzzers that are online. Then we just pick a random one with a random number generator and hand out the test case to all fuzzers of this particular type. So basically, this get available fuzzers gets all the different types of fuzzers. You can also split this up in a different way. So there's different APIs for how to hand out test cases to different fuzzers. Fairly simple, right? Then there's more complicated ones like let's see. We can have a look at the broadcast. Well, yeah, the broadcast one here. So this is a bit more complicated. Here it actually gets some information from the analysis passes. So as you can see here, we get a kind of an edge trace. So this is the coverage information, right? From analysis types, to do a get analysis state, do some Rust magic, and then basically we can say, okay, get the global coverage. Then we say, okay, compare the new coverage we have for this new test case that is incoming compared to the old coverage. And then we say, okay, hand out test cases if it actually improves it. So if we say, okay, the coverage increment count is equal to 0, we do nothing because there's no new coverage. Otherwise, we simply hand out the new test case to all the different fuzzers. Fairly simple, right? And this is quite powerful. It allows you to express pretty complicated scheduling policies using a few lines of code. So you can express something like hybrid fuzzing and so on. Like, we have implemented a bunch of these. So have a look at it and play around with. See if you can come up with some scheduling policy that works well. So that is for the schedulers. Let's also have a quick look at the analysis passes that we have. So basically we have there's a bunch of files here. I won't go into too much detail, but we have some helper things for you. So if you want to implement something yourself, it's quite easy to extend this. So we've implemented like for gathering coverage. It even has nice tests and so on. And like here, so let's have a look at one of these analysis passes. So let's see, yeah, here the basic block. So it looks at some tainting information, I guess. So I won't go into details, but basically it starts up instrumented binary and gathers some output from that binary and then saves it in a database. So, and then you can query the global database. So let's have a quick demo. Let's see how to run CollabFuzz. On the right, you can see my terminal on my server. So I'm in this folder where I have set up some useful scripts to run this demo. So first of all, there's this setup script which runs one of the tools we have, like the CollabFuzz compose tool, which generates Docker compose files to run a single campaign. So for example, this command here, CollabFuzz compose FAFL QSIM, will say, okay, set up a fuzzing campaign with AFL and QSIM. Then you can say which scheduler to use. We use the nfuzz scheduler, and then you see the target program that you want to run. So we run JSON here. So basically, let me run this. Okay, now it generated a Docker compose file. Let's have a look at this one. It's there's quite a lot of information in here. Don't worry. It simply says, okay, start up QSIM, driver for QSIM, and AFL, and driver for AFL, and so on. So okay, and then, well, we can run it by just doing Docker compose. So let's run this. Okay, now it's starting up the containers, and we're waiting. Okay, and then you can see the output, and as you can see, the framework is printing some output here. It's actually getting in test cases generated by QSIM and AFL. So it's in debug mode, obviously, as it's printing a lot of output. Useful for debugging, right? But yeah, so that's how you run a single campaign. And then, yeah, you can simply stop it. And the nice thing about this is, yeah, you can run it on a cluster because it's simply Docker Compose. So it's quite easy to set up. Then let's wait for this to die down. Okay, so that was the quick demo of a single campaign. Well, I was talking about repeatability of experiments with YAML files. So here you have a larger YAML file which says, okay, let's use a bit more fuzzers and repeat the experiment 5 times and so on. So now we can actually run this. We have a different tool called CollabFuzz run, which takes as input a YAML file. So let's do this one. And what it will do, it will generate a bunch of these individual campaigns and just add them to a queue and run them all. So it will repeat the single campaign 5 times. So, well, here we don't show all the output because it's obviously so you will be able to parallelize these experiments. And finally, I would like to conclude this talk. You've seen CollabFuzz, which allows you to orchestrate collaborative fuzzing campaigns, large-scale ones in a distributed setting. It allows you to easily implement scheduling policies. You can express very wide variety of scheduling policies. They're quite easy to implement, and you can do real-time analysis of large-scale fuzzing campaigns. So you can actually add your own analysis passes here, and which should be a nice contribution, I think. So feel free to open pull request if you have some new analysis pass you want to integrate into CollabFuzz. And finally, I would like to say that, go have a look at the source code on GitHub, check it out, play around with it. Thank you very much for listening to this talk. I hope you enjoyed it.